we define an RNN cell that basically takes in the input and the working memory from the previous step, concatenate them, and with a feed-forward neural network with a tangent hyperbolic activation returns the HT or the hidden state for the next step. So this is the RNN cell with this input and output. So we discussed that this hidden state is more like a short-term memory. And there are many nonlinear repeated weight multiplication on its way that makes the backpropagation really difficult. One idea here is to keep another state that is like the cell state that acts like a conveyor belt, does not have any repeated nonlinear overrides and multiplication like the other one. So the cell state is like the long-term memory. So CT-1 will have some addition from the input data and the short-term memory. Let's just for now call it delta at time t, updates the CT-1 with this addition, and that gives us CT. This allows the information and gradients to flow largely unchanged, as there are no weights directly modifying the main pathway. But if we think of long-term memory like a limited amount of memory that we want to use wisely in a way that complements the short-term memory or the hidden state, we want another gate that basically forgets the past and updates it with the addition here. So think of that like a valve here that we can control its angle. The same information comes, but we reduces that to allow for an addition or an update. So this is forgetting and this is addition. Okay, so we want to engineer an architecture that does this and allows for this direct line of memory while allowing for an update on the working memory or the short-term memory. Let's do that. So let's replace this valve with a function that is changing between 0 and 1. And it's like basically a knob that allows the information to either completely flow or completely stop. It's something in between. And we have a function like that. We call it sigmoid that we will show with sigma. So we want a sigmoid function to multiply here, right? And this is it inputs the HT-1 and XT. And of course, it will have a set of weights. For not making the picture very busy, I'm going to remove this weights, and I assume that you guys know before any of these activations, I'm going to have a weight like this. And we will see that in the code. So now let's focus on how to update the long-term memory. So again, we want to bring the information here, and this information will go through a neural network, a feed-forward neural network, and it will give us another state, right? So it will be a feed-forward neural network with a tangent hyperbolic, and that will be the new state that we want to add to the cell state. Let's call it CT hat or that delta here. Right? But we should be careful to also gate this. We want to put a valve here too. And the valve also will be a sigmoid. The flow is also gated here. What else? Here we can complete the updates here. It's a bit more nuanced because we want to use this long-term memory, right? And also, of course, this new information. So basically here, I want to think about something here that give us the input of XT and HT-1, use that input and also use this long-term memory to make an update and give us the HT that, of course, we can use for, let's say, predicting Y here, okay? So let's do that. I'm not going to make another neural network here that use tangent hyperbolic, right? I already did this here. And this information goes inside with this addition. So I'm going to just use this from here. I'm not going to do this again. I just want to put a gate from here. So just want to use a gate to control this information, which comes from here, right? So tangent hyperbolic again, that calculates the state, and it's gated by the input, and then we send this for the new HT. So if I want to write this in equation, you can think of this part here first, which takes in the inputs, and there is a neural network with a sigmoid that scales the forgetting here, right? So let's write this down. If I call this FT will be sigma of some neural network, takes in concatenation of HT minus 1 and XT, and maybe some bias. Now let's go to the next step that writes to the memory here. And of course, we have a scaling of that writing that controls the amount that we are writing. So if I call this IT, that's CT, we will have IT. So this is the input gate that chooses the amount of the candidate to be added. And of course, the candidate before that, which is a tangent H, some WC, again, the concatenation, and some bias. So then after applying the gate, we have the addition here. So let's write this down, which gives the CT, right? So this is the final CT, which is of course the gate that we applied element-wise on CT minus 1, and then the addition of the gated candidate, right? Again, element-wise. So everything is element-wise. Okay, great. So let's go back here. We want to output the new hidden state. Let's write this down. Maybe I'm going to call the gate here OT. So we have a gate, okay, and then HT will be the element-wise tangent hyperbolic of CT. That's how we built Lstm. So as you saw, Lstm first is relying on this two activation function, the sigmoid, that acts like a controller that controls the amount of flow and squashes the input into this range of 0 to 1. You can interpret the output like a percentage on how much information to let through, like that ball valve that I initially showed. And then the next activation function, just like what we had in RNN, it's the content shaper. So this helps to regulate the values that is flowing through the network, keeps the content bounded, and of course centered around 0. So assume that the forgetting gate is basically not blocking anything, and it's like close to 1 value. And actually that's a good value to start the training, because this allowed the information to flow and the gradient can have long range values. So as you see, Lstm architecture is a bit complex. Later there was another architecture that was introduced that is known as a GRU, or gated recurrent unit, that simplifies this cell here, and it merges the cell state and the hidden state again, and it also merges the forgetting and the input gates. So there's like two valves here that in GRU they will be merged. But in GRU there will be a different gate that is known as resetting gate, and it controls how much of the previous hidden state is considered when calculating the candidate. So for example, if RT, like I said, the reset gate is near 0, it basically forgets all of the previous hidden state or ignores it. And this way it resets and treat the current input XT as the start of a new relevant sequence. So I'm going to skip GRU here, but of course it's a very useful architecture with fewer parameters. So it has 2 gates versus the 3 gates here. In the Lstm, it has only 2 gates, the RT and the merged of F and I. Okay, so with that, we can go ahead and code Lstm.